Good day everyone. For today we're going to tackle about the chapter 12, which is the fluid dynamics and its biological and medical applications. We have dealt with many situations in which fluids are static, or it is a part of fluid mechanics that deals with fluids when there is no relative motion between the fluid particles. But by their very definition, fluids flow. The examples are a column of smoke rises from a campfire, water streams from a fire hose, and blood courses through your veins. But why does rising smoke curl and twist? How does a nozzle increase the speed of water emerging from a hose? And how does the body regulate blood flow? The physics of fluids in motion, which is called fluid dynamics, allows us to answer this and many other questions. Flow rate and its relation to velocity. Flow rate, or Q, is defined to be the volume flowing past a point in time, or T. Or it is expressed as flow rate is equal to volume over time, where V is the volume and T is time. The SI unit of volume is m cubed, and another common unit is the liter, which is 1 over 1000 of a cubic meter, or 1000 cubic centimeters. For example, calculating volume from flow rate. The heart pumps a lot of blood in a lifetime. How many cubic meters of blood does the heart pump in a 75-year lifetime? Assuming the average flow rate is 5 liters per minute. The strategy is the time, or T, and flow rate, or Q, are given, and the volume, or the V, can be calculated from the definition of flow rate. The solution is solving flow rate is equal to volume over time for volume gives volume is equal to flow rate times time. Volume is equal to, open parenthesis, 5 liters over 1 minute, close parenthesis, times 75-year lifetime times 1 m cubed over 10 cube liters times 5.26 times 10 to the power of 5 minute per year. The answer is 2.0 by 10 to the power 5 m cubed. This amount is about 2,000 tons of blood. For comparison, this value is equivalent to about 200 times the volume of water contained in a 6-lane 50 meters lap pool. Flow rate and velocity are related by Q is equal to AV, where A is a cross-sectional area of the flow and V is its average velocity. The relationship tells us that flow rate is directly proportional to both magnitude of the average velocity, or referred as the speed and the size of a river, pipe, or other conduit. The larger the conduit, the greater its cross-sectional area. Figure 12.2 illustrates how this relationship obtained. This is the figure 12.2. The figure 12.2 shows that flow rate is the volume of fluid per unit time flowing past a point through the area, or the A. Here, the shaded cylinder of fluid flows past point P. in a uniform pipe in time or team. So the volume of cylinder is AT and the average velocity is V is equal to D divided by T. So that the flow rate is Q is equal to AD divided by T is equal to AV. So figure 12.3 shows an incompressible fluid flowing along a pipe of decreasing radius. Because the fluid is incompressible, the same amount of fluid must flow past any point in the tube in a given time to ensure continuity of flow. In this case, because the cross-sectional area of the pipe decreases, the velocity must necessarily increase. This logic can be extended to say that the flow rate must be the same at all points along the pipe. In particular, for points 1 and 2. Q1 is equal to Q2, then sub 1, and V sub 1 is equal to A sub 2, V sub 2. So this is called the equation of continuity and is valid for any incompressible fluid. The consequences of the equation of continuity can be observed when water flows from a hose into a narrow spray nozzle. It emerges with a large speed. That is the purpose of the nozzle. In other words, speed increases when cross-sectional area decreases, and speed decreases when cross-sectional area increases. So here is a figure 12.3. Shows when a tube narrows, the same volume occupies a greater length for the same volume to pass points 1 and 2 in a given time. The speed must be greater at point 2. The process is exactly reversible. If the fluid flows in the opposite direction, its speed will decrease when the tube widens. So in many situations, including in the cardiovascular system, branching of the flow occurs. The blood is pumped from the heart into arteries that subdivide into smaller arteries, or the arterioles, which branch into very fine vessels called capillaries. In this situation, continuity of flow is maintained, but it is the sum of the flow rates in each of the branches in any portion along the tube that is maintained. The equation of continuity is, in a more general form, becomes n sub 1 A sub 1 V sub 1 is equal to n sub 2 A sub 2 and V sub 2, where n sub 1 and n sub 2 are the number of branches in each of the sections along the tube. So in Bernoulli's equation, the relationship between pressure and velocity in fluids is described quantitatively by Bernoulli's equation, named after its discoverer, the Swiss scientist Daniel Bernoulli. Bernoulli's equation states that for an incompressible frictionless fluid, the following sum is constant: P plus 1/2 PV to the power of 2 plus PGH is equal to constant, where P is the absolute pressure, big letter P, and the smaller p is the fluid density, V is the velocity of the fluid, h is the height above some reference point, and g is the acceleration due to gravity. So if we allow a small volume of fluid along its path, various quantities in the sum may change, but the total remains constant. Subscripts 1 and 2 refer to any 2 points along the path that the bit of fluid follows. So the Bernoulli's equation becomes P sub 1 plus 1/2 PV power of 2 sub 1 1 plus PGH sub 1 1 is equal to P sub 2 plus 1/2 PV power of 2 sub 2 plus pgh sub 2. Moreover, Bernoulli's equation is a form of the conservation of energy principle. So, pgh is also stands for the gravitational potential energy per unit volume. Another important situation is one in which the fluid moves but its depth is constant. That is, h sub 1 is equal to h sub 2. Under that condition, Bernoulli's equation becomes p sub 1 plus 1 half pv to the power of 2 sub 1 is equal to p sub 2 plus 1 half pv to the power of 2 sub 2. Situation in which fluid flows at a constant depth are so important that this equation is often called Bernoulli's principle. It is Bernoulli's equation for fluids at constant depth. So in Bernoulli's principle, the terms involving depth or the height subtract out from the Bernoulli's equation. So this is the formula. So this is the result in Bernoulli's principle. So moreover, Bernoulli's principle has many applications including entrainment, wings, and sails, and velocity measurement. So entrainment, people have long put the Bernoulli principle to work by using reduced pressure in high velocity fluids to move things about. With a higher pressure on the outside, the high velocity fluid forces other fluids into the stream. So this process is called entrainment. Entrainment devices have been in use since ancient times, particularly as pumps to raise water small heights, as in draining swamps, fields, or other low-lying areas. While in wings and sails, the airplane wing is a beautiful example of Bernoulli's principle in action. So the wing is tilted upward at a small angle and the upper surface is longer, causing air to flow faster over it. The pressure on top of the wing is therefore reduced, creating a net upward force or lift. Wings can also gain lift by pushing air downward, utilizing the conservation of momentum principle. The deflected air molecules result in an upward force on the wing, which is called the Newton's third law. Sails also have the characteristic shape of a wing. The pressure on the front side of the sail is lower than the pressure on the back of the sail. So this results in a forward force and even allows you to sail into the wind. And lastly, velocity measurement shows two devices that measure fluid velocity based on Bernoulli's principle. So the manometer is connected to two tubes that are small enough not to appreciably disturb the flow. The tube facing the oncoming fluid creates a dead spot having zero velocity, which is v sub 1 is equal to 0 in front of it, while the fluid passing the other tube has velocity for the v sub 2. This means that Bernoulli's principle as stated in p sub 1 plus 1 half pv to the power of 2 sub 1 is equal to p sub 2 plus 1 half pv to the power of 2, and sub 2 becomes p sub 1 is equal to p sub 2 plus 1 half pv to the power of 2 and sub 2. Lastly, the most general applications of Bernoulli's equation. So, power is the rate at which work is done or energy in any form is used or supplied. To see the relationship of power to fluid flow, consider Bernoulli's equation, which is the P plus 1 half PV to the power of 2 plus PG8 is equal to constant. All three terms have units of energy per unit volume. Now considering units, if we multiply energy per unit volume by flow rate or volume per unit time, we get units of power. This means that if we multiply Bernoulli's equation by flow rate or Q, we get power. In equation form, this is open parenthesis P plus 1 half PV power of 2 plus PGH close parenthesis times Q is equal to power, where the first term is power associated with pressure, the second is power associated with velocity, and the third is power associated with height. So each term has a clear physical meaning. For example, PQ is the power supplied to a fluid, perhaps by a pump, to give it its pressure, or P. Similarly, 1 half PV to the power of 2, Q is the power supplied to a fluid to give it its kinetic energy, and PGHQ is the power going to gravitational potential energy. Power is defined as the rate of energy transferred, or E over T. Fluid flow involves several types of power. Each type of power is identified with a specific type of energy being expended or change in form. And that would be all. Thank you.